Hello guys, this is Praveen Kumar Sharma, Assistant Professor from Department of Electronics and Communication Engineering at Jaipur Engineering College and Research Center, JCRC Foundation, Jaipur. So today I am going to discuss about antenna radiation pattern, which is a topic of subject antenna and wave propagation. So first, what is an antenna? Antenna is a device which is used to transmit or receive any electromagnetic signal which contains any information. It's a you can say transducer which converts the electromagnetic wave into an electronic signal which carries any information. So antenna is a device, and the radiation pattern is a quantitative measure or a graphical representation of specific antenna to describe its behavior or nature, that in which direction it will work and how it will work. So first come to radiation. Radiation is the term used to represent the emission or reception of the wavefront or EM signal at the antenna. Radiation pattern is a graphical representation of the distribution of radiated energy into space as a function of direction. Practically, the antenna does not radiate uniformly in all the directions. The radiation pattern shows the distribution of radiation energy as a function of angle about the antenna in three-dimensional space. The strength of radiation is usually measured in terms of field strength, power density, power gain in decibels, with respect to the reference level, which is usually the peak of the main beam or main lobe, or radiation pattern from the isotropic antenna in the same direction. So it is a complete field strength analysis at all the angles theta and phi in spherical coordinate system, which requires a three-dimensional presentation. In practice, it is very difficult to analyze in a spherical coordinates or a three-dimensional system, so it is common to present a cross section of the radiation pattern by a plane in two principal planes of interest, and that is called 2D radiation pattern. So as it is, the ideal or standard radiation pattern is the 3D plot of the gain, but usually it is very difficult, so we use 2D horizontal or vertical cross section of the radiation pattern for the consideration. It refers to the variation of relative amplitude of the radiation as a function of direction. As we can see, these are the formulas to find out the values or amplitudes of the points to be marked in the 2D plot, 2D radiation plot, which is a function of theta and phi. Isotropic antenna. So before coming to isotropic antenna, I want to discuss one more thing, that how we measure the radiation pattern or how we calculate the radiation pattern. So what we do practically, we take an isotropic antenna or omnidirectional antenna, which is being used as a source antenna or reference antenna, and then another antenna is a test antenna, which is placed at some distance from the omnidirectional or reference antenna. Now we start radiating a constant signal from the reference antenna and receive the signals at the test antenna. So we know what we are transmitting, what signal we are transmitting, and observe the received signal at the test antenna. At that particular angle, we get a transmitted signal gain power and received signal power. So we calculate the gain for the test antenna, that in what proportion it is receiving the energy at that particular angle. Now start rotating that test antenna with any step size you can take it at 5 degree, 10 degree, 15 degree of step size. At every that step difference, we take the observation of received power, and thus we get the gain or field strength ratio with respect to the standard or reference antenna at each and every angle points. Draw it on a 2D plot, polar plot, and we get the radiation pattern. Now, what is isotropic antenna? It is an hypothetical antenna. Practically, it is not possible. Practically, it does not exist in the real life, where it is used as a measuring bar or reference antenna for real antenna or test antenna characteristics. It's a point source that occupies a negligible space, has no directional preference. It radiates each and every direction with the equal amount of energy. Its pattern is simply a sphere. Its radiation pattern is simply a sphere. So it has omega, or the directivity angle is 4 pi steradian. As you can see, when we integrate it from 0 to pi and 0 to 2 pi, it becomes 4 pi. This is omnidirectional pattern. It means if we cut it with an plane making by xy axes, then we get equal radiation at each and every angle. It means it radiates equal amount of energy in all the directions. That's why it is called omnidirectional. Means it is not any direction specific. At all 360-degree angles, it radiates equal amount of the energy. In 2D plots, I already told you that how we make. For 3-dimensional spherical radiation pattern is cut by a plane, and we get the 2D plot. It can be obtained from the dividing into horizontal and vertical planes. The resultant pattern are also known as horizontal and vertical patterns respectively. As we can see, it is a polar plot of the omnidirectional antenna in H and B planes. This is 3-dimensional polar plot. It has major components: main lobe or major lobe and minor lobes. Minor lobes consist of side lobes and back lobes. HPBW and NNBW is half power bandwidth and null bandwidth. It's an power pattern, and that's why we are taking 0.5 from the peak, because we need half power bandwidths. Half power means where the system consists of half power. So maximum power is considered as 1. So 0.5 is for the half power, and the angle respective to that is half power bandwidth. This is angular plot. When we draw the angles on a straight line instead of circle, then it becomes angular plot. Same when we consider the power plot for half power bandwidth, we come to the half power of the maximum power. When we go for energy plot, we do it 0.7 times of the maximum energy to become get the half power points. And when we consider the power gains, in that case we come 3 dB below from the top point, and respective points are called half power points. Why we do this kind of thing is that when we need to calculate the gain at half hours, so that is 10 log 0.5 or 20 log 0.707, and that is equal to 3 dB. That's why we come 0.5 times in power gain, 0.7 times in energy gain, and 3 dB in gain plots. 0.5 in power plots, power radiation plots, Energy radiation plots 0.7 times of the maximum, and the gain plots 3 dB from the maximum. Now come to lobe formation. It's the analysis of the radiation pattern. In the representation of radiation pattern, we often come across different shapes which indicate the major and minor radiation areas by which the radiation efficiency or quality of the antenna is to be known. This is a sample radiation pattern of dipole antenna. Majorly these consist of main lobe, side lobe, back lobes. Side lobe and back lobes are minor lobes and main lobe is the major lobe. The radiation pattern has main lobe, side lobe and back lobes as I told. The major part of the radiated field which covers a large area is the main lobe or major lobe. This is the portion where maximum radiation energy exists, and the direction of this lobe indicates the directivity of antenna. The other part of pattern where the radiation is distributed sideward are known as side lobes or minor lobes. These are the areas which waste the power, or the power get wasted in these areas. There is other lobe which is exactly opposite the direction of main lobe or major lobe. It is known as back lobe, which is also a minor lobe, and this is also the wastage of energy. It is also in sample antenna pattern, which consists of major lobe, minor lobes, side lobes and back lobes. Now we come to some standard antenna and their radiation patterns. This is the half wave dipole antenna and its radiation pattern, which is bidirectional, and then another one is half wave folded dipole antenna and its radiation pattern. It's Yagi-Uda antenna, which is generally used for the TV transmission, and it is unidirectional antenna. In one direction it has the maximum gain, and in the rest other directions its gain is negligible or not considerable. This is short dipole antenna and its radiation pattern. This is V antenna with its radiation patterns. It is also a bidirectional antenna, and the resultant directivity is as shown in the radiation pattern. This is the rhombic antenna and its radiation pattern. It is also in unidirectional antenna, as you can see. Stranded antenna with radiation pattern. This is loop antenna and its radiation pattern at different elevations. When we put it at horizontal direction, then the radiation pattern is in the shape of 8, and at the angle of 60-degree elevation it becomes the circular radiation. This is an helical antenna and its radiation pattern. It is also in bidirectional antenna. This is horn antenna with its radiation pattern. It's also unidirectional antenna in single direction and with very good directivity. This is a microstripping antenna and its radiation pattern. These are parabolic antennas, and their respective radiation pattern depends on the different location or different type of waves it is receiving. This is log periodic antenna. Its branches get scaled in the logarithmic scale, and it is unidirectional antenna. This is its radiation pattern, and many more. There are infinite number of antennas and their specific radiation patterns which can be measured and can be studied. Thank you very much. Thanks a lot.